This video is going to look at the cross product of two vectors. We talked about the dot product before of vectors in 2 space and in 3 space, but now we're going to look at the cross product of two vectors, and if we're doing that, the cross product is only true in 3 space. So if we have two vectors here, the first one we'll call u sub 1 I plus u sub 2 j plus u sub 3 k. So vector u is u1 plus u2 plus u3, and then our second vector v, we'll call that one v sub 1i plus v sub 2j plus v sub 3k. So keep in mind here really what we're talking about is in more of the component form, we're basically having vector, the component u sub 1, u sub 2, and u sub 3, or v sub 1, v sub 2, v sub 3. So whether we write it in I, j, and k or here in component form, this is our here we have our two vectors u and v, and the way we define the cross product is u cross v, and we're going to set this up as finding the determinant. And the first row is simply going to be I, j, and k. And then the next two rows are going to be our vectors. So the first vector, we'll call that one u1, u2, and u3. And then we have v1, v2, and v3. So here we need to calculate the determinant of this 3 by 3 matrix. So to do that, we recall we're actually going to start here with I. And the way we can do this is block out the first row and the first column, and we're left with the 2 by 2. So we would have u sub 2, u sub 3, v sub 2, v sub 3. And because we were looking at I, this is going to be multiplied by I. And then it's going to be, as far as the formula goes, this one is always minus. The second one is always minus. And we would again look at the j part. So we're going to cross out the first row and the column that contains j. And now we have u1, u3, and v1, v3. So essentially we're breaking this down from a 3 by 3 into 2 by 2. And again, this is the j, so this would be multiplied by j. And then we would continue along with the same thing, but we would now have the next one's going to be plus. So if you notice here, the signs here are going to go plus, minus, and plus. And the k now, we're going to cover up again the first row and that last column, and we're left with u1, u2, and v1, v2. And that's multiplied by k. So there we have now broken down our 3 by 3 into 3 2 by 2s. And now if we recall, how do we find the determinant of a 2 by 2? Well, if we start here with the first one, we're going to cross multiply. So we're going to take u2 times v3 and then it's going to be minus v2 times u3s. And then that's going to still be multiplied by I. And then our next one, again, we have the minus sign. So now we have, again, we're going to cross multiply here. So that's going to be u1 v3 minus the cross up now v1 times u3. And then for the last one, we do the same thing. Plus, we're going to cross multiply. So again, that's u1 v2 minus v1 u2. And again, that's multiplied by k. And this would be your answer. Now, we would actually be able to take u2, v3. Those are going to be numbers minus v2, u3. So you're going to end up with some number times I, and then minus some number, whoops, and I left off here. This should be times j. And then we have another number here times k. So therefore, we end up with our cross product. Now, remember, when we did a dot product, when we took and said the dot product, remember we said was u dot v the answer turned out to be a scalar. It came out to be a single number. Now, when we're looking at the cross product over here, notice our answer is not a scalar. It turns out to be another vector. And once again, this is only true for the cross product, is only true in 3 space when we have I, j, and k. So let's apply this to an example here. Let's say that we have the two vectors u is equal to 4, -2, 6, and v is equal to, let's say, -1, 5, 7. And if we want to find u cross v, once again, this is going to be equal to the determinant of the I, j, k. And then we're going to write down our vectors here. We would have 4, -2, 6, -1, 5, and 7. So once again, if we go to break this down, if we start with I, we'll cross out the row that contains I in the column, and we're left with the 2 by 2 of -2, 6, 5, 7, and that's multiplied by I. And then we know the sign for this one's going to be minus, and then we're going to break this into a 2 by 2, so we cross out J, the column and row, so we're left with 4, 6, and -1, 7. That's multiplied by J. And then we go to the K, and we're left with 4, -2, and -1, and 5. And that's our K component. So now we need to break down each one of these by simply finding the determinant here, which again we're going to cross multiply. So in doing so, we're going to take -2 times 7. So we would end up here with a -14, and then the formula is minus 5 times 6, which is 30, times I. And then this one is minus, and then we would have 4 times 7, which is 28, minus -1 times 6, which would be a -6. So be careful with the negative here because the formula is minus, and then we have a -6. So that's going to be times J. And then the last one, of course, 4 times 5, we would end up with 20 minus -1 and -2 would be +2, and then that's times K. So if we go back and simplify this, then we would have -14 minus 30, so that would be a -44I, and then we have minus 28 minus a negative, so that's 28 plus 6, which would be equal to 34J. And then the last one here we have plus 20 minus 2 would be 18K. So you'll notice here when we find the cross product, the answer is another vector. And of course, we could write this in the component form such as -44, -34, and +18. So either way, we could write the answer in terms of I, J, and K, or just simply put this in the component form. Now, when we find the cross product, something else that's happening here is this vector is going to be perpendicular. Okay, in other words, it's going to form a right angle with these other two original vectors. So however these vectors are in space, this new vector from the cross product is going to be perpendicular to both of them. For an example, if we think of having our x, y, and z axis here, then we said that we have our unit vectors I, j, and k, where I is 1 unit this way and j is 1 unit this way. So here we have I and j. So what that means, if I was to take I cross j, if I was to take the cross product of I and j, that's going to be equal to k. And k is the vector, remember, that's going to go in the z direction. So here's k, and notice it is perpendicular where it forms a right angle with both vectors I and j. And that's true for the vector up here. And this is kind of hard to graph, but negative 44, negative 34, and 18, that vector is going to be perpendicular to both u and v. Okay? Now, another thing we have with the cross product is it's a way that we can actually calculate the area of a parallelogram. For an example, if we have two vectors, and we could call these, and let's see, we'll write them in component form here. If we have the two vectors, let's say 1, 2, 2, and v is equal to 1, 0, 1. Now, what we're going to do is we're going to say that if u and v are representing the sides of adjacent sides of a parallelogram, for example, maybe here we have, if this is vector u, and then maybe this here is going to be v, then if we want to find the area, okay, these are adjacent sides that make up a parallelogram, the way we can find the area of this parallelogram is by looking at the magnitude of the cross product. And that's going to be equal to the area of the parallelogram. So, if these are our two vectors that are given, then first of all, we want to find the cross product of u and v. And once again, we would have our 3 by 3 determinant here. So we would have I, j, and k. And we'd write down the vectors 1, 2, 2, 1, 0, 1. And once again, we go through the process here. We would cross out the row and the column. So we're left with 2, 2, 0, 1. That's times I. And we'll have to remember the second one has a minus sign. And we cross out the j, and we're left with 1, 2, 1, 1 times j. And then for the last one, we cross out the k, and we're left with plus 1, 2, 1, 0 times k. And now we find the determinant of each one of these by the cross product. So 2 times 1 we end up with is 2. 0 times 2, so that's minus 0 times I. And then of course this one's minus 1 times 1 is 1. Minus 1 times 2 is 2. And that's multiplied by j. And then we have plus 1 times 0 is 0. Minus 1 times 2 is 2, and that's our k. And if we simplify this, then we would end up with 2i. And then we have 1 minus 2 is a negative, but then the negative out here makes it positive. So this would be a positive 1j, or simply just j, minus, we have plus a negative 2 here, so that's minus 2k. So this here is our vector, the cross product of u and v. So now we need to actually find the magnitude of this vector. Well, we're going to do it the same way we found the magnitude of any vector here. So that's going to be the square root of 2 squared plus 1 squared plus a negative 2 squared. So here we would end up with the square root of 4 plus 1 plus 4. So that's going to be, 4 plus 1, negative 2 squared would be plus 4. So there we end up with the square root of 9. And then, of course, the square root of 9 would be equal to 3. So here we have the magnitude of this vector we said is 3. So this actually turns out to be the area of our parallelogram here. And so that gives us the area. If u and v are representing the adjacent sides of a parallelogram, then we have just found the area of this particular parallelogram. And because it's area, you want to keep in mind the answer would be 3 square units. Now here we weren't given, if it was inches, it would be 3 square inches, or if it's feet, it would be 3 square feet. So once again, keep in mind here the cross product. You're simply setting up, finding the determinant of this 3 by 3 matrix. And as we break it down, your product is going to turn out to be a vector. And one thing we have here is if we multiply the two vectors together, keep in mind that the new vector from the cross product is going to be a vector that will be perpendicular to the other two vectors. And if we take the magnitude of that vector, if u and v are the adjacent sides of a parallelogram, then that magnitude is going to be the area of that parallelogram.